Okay, Bansri, got to know. Okay, so in last class we discussed about preparation of haloalkane from alcohols. Right, these methods are not useful for haloarene compounds as we discussed earlier because of partial double bond character present between carbon and a hydroxyl group, and it's difficult to break that bond. Now today we'll study about preparation of haloalkane haloarene from hydrocarbon compounds. Now these hydrocarbons they comprises alkane, alkene, alkyne, then arenes. So from all these different compounds we'll prepare haloalkane haloarene compounds today in this class. Already I inform you to go through free radical mechanism. So second type of preparation compounds used are from hydrocarbon. In that first we'll study halogenation method. Now, what do you mean by halogenation? Write in comment box fast. Yes, Manan, Drumel. What do you mean by halogenation? What do you mean by halogenation? Yes. Yes, addition of halogen group. Anyone else? When I'm telling you to alkane, if you have to add halogen, that is halogenation. So which type of reaction is this? Substitution, addition? No, Karthik, this is not addition of halogen compound. Halogenation of alkane. Yes, Priyal, correct. This is substitution reaction. Addition, halogenation of alkane is a type of substitution reaction. Here we are replacing one hydrogen by the halogen group. So this is substitution reaction. I inform you to go through halogenation reaction given in hydrocarbon chapter. The same reaction here we are going to study again, but here we are not going to go in depth. We are not going to discuss about mechanism over here. We'll just go through the reaction fast. So halogenation of alkane, the name itself suggests that two alkane compounds here will add halogens. So alkane, which is my CnH2n plus 2, for example methane, ethane, etc. Now to this we are adding halogens, that is X2, in the presence of H mu, which is sunlight, in the presence of sunlight. Now when I expose this halogen to sunlight, what will happen? Formation of blank. Formation of blank. Reply fast. What will form if halogens they are exposed to sunlight? Yes, Brunda, correct. Free radical formation. What do you mean by free radical? Fast. What do you mean by free radical? Yes, Hitansi, free radical. What do you mean by free radical? With odd number of electrons, one unpaired electron, correct. Free radical is a species with one unpaired electron or odd number of electron. So these elements, they are known as free radicals, and these species, they are very much unstable. So as soon as they form in the reaction mixture, they attack to the next reagent. So here alkanes, when we expose to free radical which is formed by exposing halogens in the presence of sunlight, they form haloalkane compounds. They form haloalkane compounds. Let me take example of methane. Methane, when we expose with chlorine in the presence of light, this chlorine undergo homolytic cleavage to form free radical. So I have two chlorine free radicals formed. This chlorine free radical, being unstable, attack on CH4 molecule. Here from CH4 one hydrogen free radical comes out. So that hydrogen free radical combined with chlorine free radical to form HCl. Now this molecule is stable. What else form when CH4 is losing one hydrogen free radical? So CH3 free radical. This CH3 free radical formed during this reaction combined with chlorine to give you CH3Cl. But this reaction will not get stop over here. This remain continue. Again the next chlorine present in the reaction mixture, again this undergo homolytic cleavage. One more hydrogen comes out from this methyl free radical, form CH2 free radical. Here we have CH2Cl2. Again there is attack of Cl2 on the dichloromethane, formation of CHCl3 trichloromethane. Again this get attacked by another Cl2 in the presence of light. So the final product form is CCl4, and the reaction gets stopped automatically at this stage, as now there is no more vacancy for addition of chlorine to the carbon. So this is the final product which is formed. At no any stage, if I want to stop this reaction, I can. And this is the disadvantage of this reaction. This is the reason we are not using this reaction much. But this is also one of the reaction for formation of haloalkane compounds. Here, whenever we do this reaction, we'll get complex mixture of products. Suppose instead of methane, if I have CH3, CH2, CH2, CH3, let me take propane, and we undergo for chlorination reaction. Now here I have two different types of carbon atoms, terminal carbon and middle carbon. Both the terminal carbons, they are having same nature. So terminal carbon and middle carbon. So if chlorine attached to the terminal carbon, then the product form is CH3, CH2, CH2, Cl. Even there is equal chances for formation of CH3, CH, CH2, CH3, right? So possibility is there that both the products will form, and they will form in the reaction mixture. They will form in the reaction mixture. But again, here one product is present in majority while another one is present in minority. Now, as per your concepts, if I say A to this product and if I say B to this product, which one is present in majority and which one is present in minority? Write in comment box fast. Yes, which is Ash. B will be the major one. Why? Your answer is correct, but why? Yes, Brunda, B. Correct. Priyal, correct. Why B is the major product? See, here in this case, if I remove this chlorine, right, then Cl free radical and this is CH free radical. Again, if I remove this one, then CH2 free radical, Cl free radical. Which type of free radical is A and which type of a free radical is B? Leave Cl free radical. I'm talking about the alkyl free radical form after leaving the Cl from the product. A is which free radical and B is which free radical? Primary, secondary or tertiary? Write it fast. Yes, A is 1 degree, correct Ash. A is primary free radical because this carbon is attached to only one alkyl chain, and B is a secondary free radical because this is attached to two alkyl chain. Which one is more stable, primary free radical or secondary free radical? Write fast. Yes, Krish. Secondary free radical is more stable in comparison to primary free radical. And as per this rule, Ash, wrong. Secondary free radical is more stable in comparison to primary free radical. And this is rule that the one which is more stable will form with more faster rate. And as per that rule, secondary free radical being more stable, product B forms in major quantity while product A form in minor quantity. Got it? So here product B will form in major quantity. So as you see in this case, the product you get is a complex mixture of isomeric mono and poly haloalkane compounds. And these compounds, their boiling point, melting point values are very nearby to each other, and because of this it's very difficult even to separate pure compound from this. And because of this, yield of one particular product is very low. So this is the reason this is the least used method, halogenation of alkane. Next method we have to study, that is in hydrocarbon only, that is by electrophilic substitution. If I take arene, arene is my benzene, and for this if we add Cl2 or Br2 in presence of Lewis acid catalyst, which is of iron, or I can say Fe3 chloride, FeCl3, then here I'll get either aryl chloride if I have added Cl2 or aryl bromide if I have added Br2. Now this is the product form. This is the product form over here. Now here electrophilic substitution reaction. Why it is so? So here I am taking Cl2, which is in presence of FeCl3 convert into electrophile. What you mean by electrophile? The one which has attraction towards electrons. Your benzene ring is electron rich ring because of presence of 3 pi bonds. Because of presence of 3 pi bonds, your benzene ring is electron rich ring. So electrophile is going to attack on electron rich benzene ring. Now here this benzene is having 6 carbon with 6 hydrogen atom. So when electrophile attack, that is replacing one hydrogen and attaching itself. So this is electrophilic substitution reaction. So here this electrophile form, if this is a chlorination, Cl plus is electrophile. So this Cl plus is going to attack on the benzene ring and product form is chlorobenzene, and so this is electrophilic substitution reaction because this replace hydrogen and get attached at the place of hydrogen, chlorine. Now to this reaction, if I say electrophilic substitution reaction, then name of the reaction for CH4 attack on chlorine, Cl4 get attacked by chlorine and there is formation of CH3Cl. Give me name of this reaction. Give me name of this reaction. Fast. As per electrophilic substitution reaction, if I have to give name to this reaction, what is name of this reaction? Write in comment box. No any comment till now? Name of this reaction, if this second reaction, yes, this is substitution, but is this electrophilic substitution? No. Yes, Vrunda, correct. This is free radical substitution reaction. Good. This is free radical substitution reaction. So here we are studying electrophilic substitution reaction, while the first one is free radical substitution reaction. Now here also we may get ortho and para isomers, but these isomers you can easily separate out because of there is difference in their melting point. So due to difference in melting point, you can easily separate out these products. Now, is there any chance that here if I have di-substituted product, formation of meta isomer is there? Write in comments box yes or no. Meta isomer formation is possible or not? Meta isomer formation is possible or not? No any comment? No, meta isomer is not possible over here. Only ortho and para formation is possible over here. In detail, we already discussed in when we study about ortho para meta directing groups in hydrocarbon chapter. Now here I discuss you about chlorine and bromine. What about iodines? So reaction with iodine here in this case is reversible. Here reaction with iodine is reversible. So what we need to do is here the HI which is formed as byproduct, this required to oxidize. So here we require presence of oxidizing agent. Why? For reaction? No, not for reaction. To oxidize the HI formed during the reaction. To oxidize HI formed during iodination reaction. What about fluorination? So for fluoro compounds, we can't prepare them by this method. We have alternate method. So we need to take toluene, which is benzene ring with CH3. Again, this is ortho-para director group. So when we treat this with halogen in the presence of iron catalyst, this undergo halogenation reaction, again substitution reaction. Iron, again convert this to electrophile. I have electrophilic substitution reaction. So here I have CH3 group. These two are ortho positions and this is para position. So in one case I'll get ortho product and in another case I'll get para product. So ortho halo toluene and para halo toluene, these two products will obtain at the end of electrophilic substitution reaction. Third type of reaction here we have to study, that is Sandmeyer reaction. This is named reaction, very important reaction for exam purpose, board exams, even competitive exams. So when we take aromatic amine like aniline, aniline is benzene ring with NH2. This reaction even we are going to perform in lab when we go through organic qualitative analysis. So this is aniline. When we treat aniline with sodium nitrite NaNO2 plus mineral acid like HCl at 0 to 5 degrees Celsius. So we need to carry out this reaction in ice bath, 273 to 278 Kelvin. Then this aniline convert into benzene diazonium chloride. Benzene diazonium chloride. See here we already having one nitrogen present. Two hydrogens, they get replaced by another nitrogen and chlorine. So here we have N triple bond N plus Cl minus. As these nitrogens forming 4 bonds, maximum capacity is of 3 bonds. So with one positive charge, because it's sharing its lone pair of electron, and that's why positive charge. So this is benzene diazonium chloride. In short, this is also known as BDC. This is very important product because this is the one from which you can prepare many of the mono-substituted benzene derivatives, and this is the reason this BDC is very important for us. So aniline to benzene diazonium chloride formation by addition of NaNO2 sodium nitrite plus mineral acid to the aniline, and this reaction is known as diazotization reaction. This reaction is specifically known as diazotization reaction. Now the important step for us over here is, once we have formation of this benzene diazonium chloride, to this when we add Cu2X2, to this when we add Cu2X2, this form this whole N2 plus Cl minus get replaced by halogen, that is X. Now here X is equals to either Cl or Br. So chlorobenzene or bromobenzene, if I want to prepare, if I want to synthesize, I can use this method, Sandmeyer reaction. So this is my Sandmeyer reaction, benzene diazonium chloride to halobenzene. This is my Sandmeyer reaction. First one is diazotization reaction, but whenever there is question Sandmeyer reaction, you have to explain whole, even in board exams. If I treat this benzene diazonium chloride with Ki, potassium iodide, this is not Sandmeyer reaction, then the product form is aryl iodide, iodobenzene. If I treat benzene diazonium chloride with potassium iodide, then the product form is iodobenzene. That's it. What is about Sandmeyer reaction? Next we have formation of haloalkane from alkene compounds. Alkene is C double bond C type of compounds. So here also we have two sub methods. One is addition of HX. This also you already studied in case of hydrocarbon chapter, alkene, chemical reactions of alkene. Alkene, if I have ethene, when I treat this with HX, the product form is the double bond get open up. From here I have cleavage of this reagent. One will get added up to the one carbon, another one will get it added up to the another carbon. Even if reverse case is there, the product form is same. There is no any difference, and the product form is haloalkane. Here I had symmetrical alkene. What if I have CH3, CH, double bond CH2, and to that if I add HX, the product form is question mark. Apply Markovnikov's rule and write the product form in comment box fast. Alkene plus HX gives what? No reply. Alkene plus HX according to Markovnikov rule, which is the major product? CH3, CH2, CH2, X plus X. Yes, Shreya, your answer is very correct. Ash, your answer is also correct. Hitanshi's answer is wrong. This is according to NT Markovnikov, the answer which you have written. According to Markovnikov rule, the one which is negatively charged goes to the carbon having less number of hydrogen. Here halogen is, yes, Sanskruti. According to Markovnikov rule, X is negatively charged, and negatively charged ion goes to the carbon having less number of hydrogen, and as per this rule, the major product form is CH3, CH, CH2 and X, 2-halopropane. Along with this, in minor quantity, we also have formation of CH3, CH2, CH2X, but the major one is this. This is the minor product form. So this is one type of addition to the alkene. Another type of addition to the alkene is addition of X2. Addition of X2. So again, if we take alkene, and to that alkene if I add X2, that is dihalogen, in the presence of solvent, that is CCl4, carbon tetrachloride. Then the product form is this, both the double bonds get open up. Double bond get open up, and on both the carbon atoms I have one halogen. So this is which type of dihalogen? Geminal or vicinal? Write in comment box fast. The product is what? Yes, correct. Vicinal dihalide. Vrunda, then Sanskriti, Urvashi, Kartik, Ash, Amisha, Rucha, Hitanshi, Priyal, Drashti. Right, correct. Now, here as a halogen, if I take bromine, actually bromine is available in lab in the form of bromine water, which is brownish in color. When I treat this both, alkene plus bromine water, then the product form is CH2 single bond CH2 Br, that is vicinal dibromide. Then this brownish color turns to colorless because of formation of vicinal dibromide. And this test we use to identify if there is presence of any unsaturation. See, this is unsaturated compound. So if there is presence of any unsaturation in the in the given compound, for that we make use of this bromine water. Here the second type, that is from hydrocarbon, preparation of haloalkane, haloarene from hydrocarbon is also over. Under that we study halogenation of alkane, then electrophilic substitution of benzene ring, Sandmeyer reaction when we treat aniline, starting reagent was aniline, and from alkene in that two types, alkene plus HX and alkene plus X2. Now the third type, that is by halogen exchange. Here our more reactive halogen will displace less reactive halogen. So Rx, when I take and treat with sodium iodide, in the presence of dry acetone, then this halogen get displaced by iodine and the formation of product is alkyl iodide from alkyl chloride or alkyl bromide. From the name of the scientist who discovered this reaction is known as Finkelstein reaction. This reaction is known as Finkelstein reaction. What if I want to prepare alkyl fluorides? See here, iodide I get by replacing chloride and bromide. If I want alkyl fluoride, that is RF, then for that we need to take alkyl chloride or alkyl bromide, and to that we need to treat with metallic fluorides. Like I can take silver fluoride, mercury fluoride, cobalt fluoride, antimony fluoride. All these you can use when you treat your alkyl chloride or alkyl bromide with metallic fluorides like silver fluoride, mercuric fluoride, cobalt fluoride or antimony fluoride, then the product form is alkyl fluoride. And this reaction, from the name of the scientist who discovered, known as Schwarz reaction. So this is what is here. We are exchanging one halogen by the other. So this method is known as by halogen exchange. So total we studied three different reagents from which we can prepare our haloalkane, haloarene compounds, that is alcohol, hydrocarbon, and by halogen exchange. Here your preparations are over for haloalkane haloarene compounds. Now we have to study about their physical property, how they look like, what about their melting point, boiling point, their solubilities and all. We'll study now. So now we'll study about physical properties of haloalkane haloarene compounds. So physical properties, so first we'll of course see how they look like. So these are colorless compounds. Physical properties of halogen derivatives. So these are colorless compounds when they are pure. But bromides and iodides, as I just say that bromine water is brown in color, here I'm telling colorless, but these bromides and iodides, they develop color when they expose to light. When they expose to light. And this is the reason bromide compounds are brownish in color and iodide compounds are violet in color. Many of these compounds are volatile. Many of these haloalkane compounds, they are volatile in nature. Volatile means they easily convert to vapors because of their lower melting point values, and because of that they have sweet smell, and even they have sweet smell. Let me discuss about their melting point and boiling point first under these physical properties. So lower members, if you see like CH3Cl, CH3Br, CH3CH2Cl, then chlorofluoromethanes, all these are compounds with very much less number of carbon atom. These are gases at room temperature. But if you go for higher members, they are either liquid or even they are solids. If we compare them to alkane compounds, in comparison to alkane, if we see haloalkane, my alkane is RH and my haloalkane is RX. Here I don't have any polarity present, while here as we see, this is polar compound, this is partially negative, this is partially positive. Then what you can say about boiling point and melting point of these haloalkane compounds in comparison to alkane, whether these compounds they have higher melting point, boiling point values or not. See, when I have to decide about melting point and boiling point, what I have to take into consideration is intermolecular attraction forces. Here the only force present is van der Waals force. While here yes, Hitanshi, your answer is correct. Here van der Waals force is there, but in addition to van der Waals, is there any other force present? Is there any intermolecular attraction force present? Yes or no? Fast. If yes, which one? Which one, Priyal? Yes, correct. Dipole forces are present. Dipole intermolecular attraction forces are present. Those who have doubt what is dipole, go through chapter 4. There initially only these forces are discussed. So along with van der Waals forces, dipole forces are also present, and because of this intermolecular attraction forces are higher in case of haloalkane in comparison to alkane. And this result in what? Haloalkanes have higher value of melting and boiling point in comparison to alkane. Now, if we talk about for same alkyl group, now my alkyl group is same, suppose for methyl, but my halogens are different. If I take Ri, Rbr, Rcl and Rf, what is trend according to you? They follow increasing order or decreasing order? Which one has least boiling point melting point value? Which one has least boiling point melting point value? Write in comment box. Which one has least boiling point melting point value? Least, I'm asking. Yes, Vrunda, your answer is correct. Yes. RF has least value. Why it is so? Here we don't have to break one. Here we only have to overcome these intermolecular attraction forces, which is van der Waals along with dipole. Right? Now RF has least because here van der Waals force predominate. Van der Waals force that depends upon number of electrons present, and number of electrons present in case of iodine is more, and so more energy is required to remove intermolecular attraction forces in case of iodine in comparison to fluorine. Fluorine has only 9 electrons while number of electrons present in iodine is more, so extent of van der Waals force is also more in case of Ri compounds, and so having highest boiling point melting point values in this case. So this is because magnitude of van der Waals force is highest in case of Ri because of more number of electrons present. Next, if we say that if I have same number of carbon containing chain and even I have the halogen present is also same, right? In that case, so I can use term for isomeric haloalkanes. Let me take butyl. So normal butyl bromide, isobutyl bromide, tertiary butyl bromide, right? So if I have normal one, if I have iso one, and if I have tertiary one, according to you, which one has highest? Which one has highest? Write in comment box fast. Normal, iso, tertiary, which one has highest? Normal, yes Vrunda, very correct. Amisha, not tertiary, normal one. Even you study this in hydrocarbon, that whenever you have branching, as branching increases, the molecule attains spherical shape. This result in what? When you have spherical shape, surface area becomes less and less amount of heat is required. So normal has highest, then iso, and then tertiary. If we see for butyl bromide, then for normal value is 375, this is 364. So why this happen? So as branching increases, surface area decreases, which tends to attain spherical shape, means required less energy. Why it is so? Still, so because contact points between two molecules decreases when branching increases. If I have two normal isobutane, all the four carbon they are in contact with each other. But when I have isobutane, and if my chain is like this, now here the number of carbon atom which are in direct contact with each other, that is only 3. This result in what? Decrease in number of contact points. Here all four they are in contact with each other, while here only 3 are there in contact with each other. So only I need to break 3 bonds when I want to boil this compound, while here I have to break 4 bonds when I have to boil this compound. So as branching increases, number of contact point between two different molecules decreases. This result in what? Decrease in value of melting point and boiling point. Now let me discuss about isomeric haloalkane. So if we talk about isomeric haloalkane, then I have 3 different isomers: ortho, meta and para. Ortho, meta and para. So if you go for boiling point and melting point for this, then meta has least, then ortho and then para. Now see, meta that is having least because of attraction forces are least in this case. Ortho and para, now we have to compare. Now in case of para, the symmetry factor, this predominant. Para molecule is very symmetrical molecule. So if I have to pack this in a crystal lattice, this fit to a very perfectly. So to break that lattice, I need more amount of energy. And so symmetry of para isomer that fits in crystal lattice better as compared to ortho and meta. So para has highest. And then ortho and meta, so these two groups are very nearer in case of ortho. So because of that, ortho has higher and the least one is meta. Least one is meta. So the order for boiling point, melting point in case of isomeric haloarenes is highest in case of para, then ortho, and the last one is meta. We come to the next factor, density. Now for density here increases with increase in number of carbon atom, then halogen atom and atomic mass of halogen atom. So of course in case of iodine density is highest, and in case of RF density is lowest. Last factor under this, solubility. As per these are polar compounds, so solubility must be very good. But here if you see, very slightly soluble in water. This is very important question in board exam, that haloalkanes are polar in nature, though they are slightly soluble in water. While soluble in organic solvents which are non-polar. So why? Let me understand this now. So these haloalkane molecules, they have very strong attraction forces because of polar nature. And water molecules, they also have forces. Which one? So hydrogen bonding. Now here we have to overcome these two forces. So if I want to dissolve these haloalkane compounds into water, what I need to do? I need to break bonds between haloalkane molecule. Even I need to break bond between water molecule. So for these breaking of bond, I require some energy. But when there is formation of bond between halogens and water molecules, energy get released. Now here in this case, to dissolve haloalkane in water, energy is required to overcome this. Right? Here I need energy. Now against to it, the energy which is released when new bonds form. Between haloalkane and water. This has to be more, but this energy is less. As here now these are not as strong as the earlier one. Original one. And because of this, these are slightly soluble. Hence, they are slightly soluble. Got it? Let me think about now organic one. While in case of non-polar solvents, which are organic solvents, the new setup, that is a new intermolecular attraction force, between what? Again, and solvent molecule. Here this is similar value. The value is similar as that once being broken in the separate haloalkane and salt. Case of organic solvent, but in water they are only slightly soluble. Hope you all get this. So this is what is about their solubility. This is one of the important question from board exam point of view, that haloalkanes are polar in nature, though they are slightly soluble in water while soluble in organic solvents. So here we'll end up with today's session. So in today's class we discuss many things. So here in today's class we discuss about preparation methods. We complete preparation methods and we even complete physical properties of these compounds. Tomorrow we'll start with the very important topic, which is chemical reactions of haloalkane and haloarene compounds. So all of you are requested to present in tomorrow's class. Even in this year board paper, question asked from this chapter is from the next topic, which is your the chemical properties of haloalkane and haloarene compounds. Bye.